Alright guys, I'm going to show you in this video how we can implement principal component analysis from scratch using just Numpy. So to start here, we've just got an empty project. We're going to add a couple of dependencies, and really the only dependency we need is Numpy, but we're also going to have scikit-learn and matplotlib because we want to compare our implementation against scikit-learn and make sure that we got it correct. So we're going to add Numpy, matplotlib, and scikit-learn. And we're going to go ahead and sync our virtual environment as well. Make sure everything's good. All right, cool. I'm also going to add ipykernel because I'm going to do this in a Jupyter notebook just to make it really easy for us to visualize everything. So I'm supposed to do UV add. There we go. So now we got everything in place and we can go ahead and get started. So we're going to do pca.ipynb. And we're going to select our kernel. Cool. All right, so the first thing we're going to do is just import everything. Let's get scikit-learn as well. And actually, really quick, looks like the IntelliSense is not working, so I'm just going to reload the window real quick. And that should fix everything. And so, going to go ahead and load this up. Oh, this is sklearn, sorry. And it's going to take a second because we just created this environment, but it's going to resolve all of these things and import them. So, we're going to do this on the iris dataset. If you don't know what the iris dataset is, it's a classic dataset for classification, and it's a great example for principal component analysis because there's a tremendous amount of variance along the first one or two principal components. So it's a very great and illustrative example. So we're importing datasets from scikit-learn. We're going to load the dataset with that module. So it's datasets.loadiris, I believe. Yep, and then we're just going to get the actual data itself, and then the labels corresponding to these to this dataset. All right, and then I mentioned that we're going to test our implementation against scikit-learn, so I'm going to make a copy of this data just to make sure we don't mess anything up, and we're going to do the exact same thing to our scikit-learn copy, and then verify that we get the same result back. So we're just going to do .copy. All right, cool. So now I've imported our data and we've made a copy of it for testing on later on. All right, really quickly, I don't want to take too much time out of the video, but this video is sponsored by me. So I offer a tutoring service if you need help in high school level math, test prep for the ACT or the SAT, or university level math. Please check out my service. I promise it'll definitely be worth it. You can book a free consultation and we can get started. Go to www.kuehrtutoring.com. That's Kuehr tutoring.com. The link is going to be in the description. Thank you guys. We're going to go back to the video now. So before we go any further, we need to do a little bit of pre-processing to the data. So what principal component analysis does is it tries to find directions within the data set which maximize the variance between the samples. And so we run into the issue where if the magnitude of certain features in our data set is wildly different, or if the offset of where all of those features are clustered is different, then that's going to skew the principal components and it's going to give us a wrong result. And so the way we get around this is that we center the data and we also put it on a uniform, well, not a uniform, but we put it on a fixed scale. And the way we achieve that is with z-score normalization. And so just to be clear, I'm not going to explain the theory in great depth in this video. This is just an implementation video. In the future, I'm going to make a video where I talk about it from a theoretical perspective, but that's not the aim here. So let's make this z-score normalization function, and we're just going to take in our x, which is a Numpy array. I'm going to do the type heading here just to make it very explicit. And we want to normalize along a particular axis. which in this case, if you think the rows are our samples and the columns are the features. If we want to normalize along the columns, our axis that we're going to go down to do so is going to be the 0 axis. And then we're going to return the same array, but just normalized. And so z-score normalization, let me just write it out for you guys. So we have some feature, let's say we have some feature x. Oh, so we've got a feature x. What we're going to do is we're going to subtract the mean of all of the observations of this variable x, and then divide by the standard deviation of x. This is called z-score normalization. And what this gives us is it gives us, first off, data that's centered. So if your data point lives on the mean, its value is now 0. If it's outside of the mean, if it's higher than the mean, its value is positive, and if it's below the mean, its value is negative. Furthermore, by dividing by the standard deviation, the actual value we get back is exactly how many standard deviations our data point is from the mean. So if we have a data point that's exactly 1 standard deviation from the mean, this is going to be 1. If we have something that's exactly 2 standard deviations from the mean, this is going to be 2, etc. And so that's the goal, is we want to make sure that the inputs that we're giving to principal component analysis are centered and also have sort of a fixed range of values that they can take on. And the point of that is so that we don't introduce bias in the covariance matrix, which is where we eventually get our principal components from. So hopping back over here, let's just implement what I just talked about. So the first thing we're going to do is we're going to take the mean of our array, and when you do mean, it lets you specify the axis if it ever loads. Not sure why the IntelliSense is being so bad, but basically we're going to take the mean of this array along this axis. And we can also calculate the standard deviation. So we're going to do x.standard deviation axis, and we're also going to pass in the mean, because we can simplify the amount of calculation that we're doing and avoid some redundant calculation by passing in the means which we've already computed. And then here's the actual step where we implement the normalization. We're going to do x is equal to x minus mean divided by standard deviation. And the way this works, even though technically this is an array, because we can use something called broadcasting in Numpy, it's going to infer the dimensions that we're trying to work over and perform the correct computation. And now finally, we're just going to return x. All right, the next thing we want to do is compute the covariance matrix. So the way we get our principal components is we compute the covariance matrix of our data, and then we ultimately find the eigenvectors of that covariance matrix. And so we're going to create a function called compute covariance matrix. It's going to take in our data matrix, and it's going to return back a covariance matrix, and we'll pass this for now. And I want to make sure I'm explicit here. You want to do the z-score normalization first before you apply this function, because if you haven't normalized your data, like I said, your covariance matrix is going to be giving you bad information. It's going to end up messing up the principal components that you would otherwise get out. And so let me talk about the calculation for covariance. So if we have two variables, we've got x and y. The covariance between x and y is, we're going to divide by 1 over n minus 1, where n is the number of samples. It's this times the summation over all observations of xi minus its mean, yi minus its mean. Oh, well, we try to make that a little better. And so this is what you get. So you're taking the centered x value at sample I, the centered y value at sample I, you're multiplying them together, and then you're summing that up over all samples I and dividing by n minus 1. And this is your covariance. And so what you'll notice is that when we are looking at our covariance matrix, it looks something like this. So we're going to have So on the principal diagonal, what we actually get is not the covariance, it's just the variance of a variable. Because when your column and row index are the same, this y here is going to become an x. And so this whole term goes away, and the first term is just squared, which is the exact formula for sample variance. And so over here, though, we've got covariance xy. This is covariance xy as well, because it's a scalar, right? So covariance xy is the same thing as covariance yx, and then so on. And so what you'll realize is that your matrix itself is a symmetric matrix. And this is going to be an important property later on. But the main thing we have to recognize here is that our covariance matrix is going to be, it's going to be of shape n by n. Well, actually, I'm already using n here, so let me say m. So if n is our number of samples and m is the number of features, our covariance matrix is going to be an m by m matrix, right? So it's number of features by number of features, and it's a symmetric matrix because covariance of xy is the same thing as covariance of yx. And so really all you have to do is compute the upper triangular portion of it, and that's what we're getting back. All right, so how do we actually do that computation? So it's pretty simple, actually. So we can leverage the fact that we're working with Numpy arrays and do something smart. So we're going to do covariance as x transpose matrix multiplied by x, and then we're going to divide by x dot shape 0 minus 1. So let me explain, and we're going to return. So let me explain what we're doing here. So remember, our default data matrix is the number of samples times the number of features, right? If we transpose that, it gives us number of features by number of samples. And therefore, x transpose x is going to be number of features by number of features, which is exactly the shape that we're expecting of our covariance matrix. And when we are doing this, each individual index in the matrix that this matrix product returns is going to be the dot product of all of the rows, or sorry, all the samples along a particular feature. So if you think we've got, in X transpose, it's going to be feature 1 is a row, and then all of the columns are the observations, are the observations of that feature. Row 2 is another feature, and then all of the columns are the observations of that feature, and so on. And so what we're doing when we do the dot product is we're actually implementing that summation from the calculation that I showed you guys. And the reason why we don't have to do the mean subtraction is because we already did that over here. And then finally, what this is just doing is we're taking the number of samples, which is the first dimension of the shape, subtracting 1, and then dividing by that. So really, all we have to do to fill in the covariance matrix is do one matrix multiplication. And you could even make this more efficient. Like I said, you really only need to find the upper triangular portion. But for the purpose of this example, this is sufficient. All right, so the way that we're going to actually get our principal components is we need to find the eigenvectors of our covariance matrix. So we have the ability to compute it now, and now what we want to do is we want to find the eigenvectors. But here, I'll go ahead and do that right now just to be instructive. So remember, we have a real symmetric matrix, so we can use NumPy's eigh function, which is more efficient for, they're called Hermitian matrices, but in the real case, it's just a real symmetric matrix. So we could do eigenvals, eigenvex equals np.eigh, so it's np.linealge.eigh, and we're going to pass in our covariance matrix. So we'll say, first we're going to standardize, right? So x scaled is equal to z-score normalization of x. And then our covariance matrix is equal to is equal to compute covariance matrix of x scaled. And so what we ultimately want to do is find the eigenvalues and eigenvectors of our covariance matrix. And so we can do all of that with these 3 lines of code. So let's actually run these cells first, so that all the variables are loaded into memory. And now we can do this. So, okay, let's look at the eigenvalues. So these are our eigenvalues. We have 4 of them, which makes sense because we have 4 features. And let's look at the eigenvectors. So it's a 4x4 matrix, but in this case, the columns are the eigenvectors. So this column is eigenvector 1, this column is eigenvector 2, etc. And so we've got our data, we have our covariance matrix, and we have our eigenvectors, which are our principal components. So what we want to do is we want to take our data and project it onto the first 2 principal components. In our situation, we just want to visualize the first 2 principal components in R2. And so let me explain what I mean by projection. So when you want to project data onto something, right? Let's say we want to do a scalar projection of some vector A onto a vector B. So we have some vector A, we have some vector B. We want to project A onto B. If B is a unit vector, so what that means is that the length of B is equal to 1, then the scalar projection of A onto B is literally just the dot product. That's our scalar projection. And what Numpy does is it actually standardizes our eigenvectors to be to be unit vectors. So what that means is that all we need to do to project some data point onto our eigenvector, which is our principal component, is just take the dot product. So coming back over here, we're going to make a new function called project PCA. We're going to take in a sample, which is going to be a Numpy array. We're going to take in our eigenvectors, which is, again, a Numpy array. And we're going to specify the number of components, which in this case is going to be 2. And this is going to give us back a Numpy array. So let's make our principal component matrix. And all we're going to do is we're just going to take the first 2 columns, right? So the first n components columns. So PCA matrix is equal to eigenvectors. We're taking the first n components columns, exactly like this. And then how are we actually going to handle the projection, right? So I just told you that if the vector you're projecting onto is a unit vector, all you have to do is take the vector that you want to project and dot it with that unit vector. And so the way we're going to do that is we're going to do np.dot our sample with our PCA matrix. So think about this, right? Our sample is going to be a 1x4 vector, and then our PCA matrix is going to be a 4x2 vector. So when you do that dot product, what we're going to end up getting back is a 1x2 output matrix, where 1 is our sample and 2 is the 2 components of that sample projected onto the first 2 principal components. And so you imagine if we call this project PCA function onto our entire data set, what it's going to give us back is it's going to give us an n×2 matrix, where n is the number of samples that we've seen. And each column, the first column is the projection of those samples onto the first principal component, and the second column is the projection of those samples onto the second principal component. So something I want to mention is that the eigenvalues of our covariance matrix are going to tell us which of the principal components explains the most variance. So the eigenvalue, which is greatest in magnitude, is going to correspond to the eigenvector, which explains the greatest variance. The eigenvalue, which is the second greatest in magnitude, is going to correspond to the eigenvector, which explains the next greatest amount of variance. And so our covariance matrix has a couple of properties. The first of which is that it's symmetric. And so what that means is that we're guaranteed to have a full set of orthogonal eigenvectors, which are our principal components. And in particular, the covariance matrix is semi-positive definite. And what that means for our purpose is that all of our eigenvalues are guaranteed to be non-negative. So at the very least, they're 0 or they're positive. And so what we want to do is we want to calculate how much each principal component is exploiting the variance. And the way that we do that is we take all of our eigenvalues and we divide them by the sum of all of the eigenvalues. And that gives us a percentage that that individual eigenvalue explains. So we're going to write a function called calculate explained variance. We're going to take in our array of eigenvalues and return back an array of our standardized eigenvalues. So we're going to take this array and divide each element by the sum of all the elements in the array. And so this is going to give us a set of numbers whose sum is going to equal 1, which we can interpret as percentages. All right, the next thing we're going to do is we're going to make a function to plot the plot our projection of our data set onto the principal components. So we're going to do this function that's going to take in our projected data points. It's going to take in y, which are the labels of those projected data points, and we're also going to take in the explained variance. That's going to help us label the axes correctly. So this actually doesn't return anything. So first thing, we're just going to create a figure. Let's just make it an 8x8 figure. And now we're going to do a scatter plot with matplotlib. So we're going to do plot.scatter. And okay, so we want the first thing we're plotting to be all of the projections of our points out of the first principal component, because we're going to treat the x-axis as our first principal component and the y-axis as our second principal component. So x projected, take everything from the first column, and then we're going to take everything from the second column. Our labels are going to be our y array over there, and the rest of the stuff doesn't matter as much, but it helps make the visualization a little bit better. All right, cool. Now let's set our axes real quick. So just doing some standard stuff here. And we're just going to do the exact same thing on the y-axis. So I'm going to copy this and do AX V line. And now we're going to label our axes. So our X label is just going to be PC1. And now we're going to show how much variance is getting explained, right? So we're going to take explained variance 0, and we're just going to format it a little bit. And the exact same thing here. So all I'm doing is just making sure that our plot that we're going to return is going to be representative of the data that we're passing into it. And so we'll give it a legend so that we can actually see what the classes of the data points that we're plotting are. So and we're just going to title it, wow, I can't type, class. And let's just title it, I don't know, let's title it PCA plot iris dataset. All right, cool. So this is the function we're going to use to plot our implementation of principal component analysis and compare it against scikit-learn's implementation of principal component analysis. Now, I deleted our previous computations and I cleared everything out, but I forgot there's one thing that I need to mention. So when you do the eigauge function in Numpy, it gives you your eigenvalues and eigenvectors in ascending order. And because we want to look at the eigenvalue which is biggest in magnitude first, we want to actually put it in descending order. And so the way we're going to do that is I'm just going to make a function called eigsort. It's going to take in our eigenvalues, and then it's going to take in our eigenvectors. And we're going to get back the exact same thing, but we're just going to sort them. Alright, so we want to find the descending indices. So we can use np.argsort here. So we're going to find the indices of our eigenvalues array, which would sort us in descending order. So we're going to put in eigenvalues, and we're going to do descending equals true. And now what we want to do is return the sorted array of eigenvalues and sort the corresponding eigenvectors in the exact same way. So we're going to do eigenvalues, descending indices, and we're going to do eigenvectors. Actually, we want to go by the rows here and then just sort the columns. So, all right. So this gives us the function to sort our eigenvalues in the way that we would expect to see them. All right. So now let's go ahead and do all the computations, and let's plot our implementation and see if it's correct. So I'm going to make a section down here for my implementation, and we'll do one beneath it for the scikit implementation, which we're going to compare against. So first thing we want to do is we want to scale the data again. So I deleted all of the previous computations where we scaled the data and computed the covariance matrix. We're going to just do it again down here. So we're going to do compute z-score normalization. Actually, I don't think it was compute. I think it's just z-score normalization of x. And then the next thing we want to do is find the covariance matrix. So remember, we're scaling first. I explained why we're doing that. If we don't scale and we just find the covariance matrix on the raw data, it's going to give us the wrong output. So we're going to do compute covariance matrix of x scaled. And now we want to find the eigenvalues, eigenvectors, np.linealg.igh of covariance matrix. Oh, I need to rerun all of this stuff real quick. All right, that should work now. And so remember, I just explained why we need to sort the eigenvalues and the eigenvectors, so we're going to do that real quick. So eigenvals, eigenvex equals eigsort, eigenvals, eigenvex. So now what we should see is that if we do eigenvalues, yep, now we're in descending order. If we do eigenvectors, we should see that now, well, I didn't print it out before, but since we sorted it in the same way, the eigenvectors are now ordered such that they correspond to the eigenvalues in descending order of magnitude. And so now let's do our plot. So we're going to do PCA plot. Oh, I forgot, we need to project our stuff real quick. So we've got our eigenvectors arranged in the way that we want to. So now we could just take, we could say x projected. We're going to project our scaled data onto the principal components. So we're going to do, let's see, project PCA. All right, so we're going to do, so we're projecting x scaled, and we're taking in our eigenvectors, which we've just sorted, and we're going to take two components, right? Because we're projecting out of the first two principal components. So now we've got x projected. We have everything we need to plot it. So we're going to do PCA plot. We're plotting x projected. Y are the labels, and then our explained variance. We can calculate that just very quickly. So let's do explained variance is equal to, I believe it was calculate explained variance on our eigenvalues. Let's print that out real quick. Yep, So this looks like it should sum up to 1, so that's exactly what we want. Alright, this is the moment of truth. Let's look at our plot. Okay, cool. So we've got our plot, and now what we want to do is we want to make sure that our implementation roughly corresponds to what scikit-learn gets. So we're going to do from sklearn.preprocessing import standard scalar. We're going to do from sklearn.decomposition import PCA. Oh, there we go. All right, so this standard scalar is going to do the same thing that our z-score normalization does. And so what we're going to do is we're going to do x scaled sklearn is equal to scalar.fit transform x underscore sklearn. And we're also going to create our principal component analysis object. And we're going to do pca.fit x scaled sklearn. So we did our fit, good. Now we're going to use my projection function just to do the same projection. So we're doing x projected sklearn is equal to project PCA x scaled sklearn. Okay, and now here's something I want to make apparent. So if we look at PCA.components, their convention is that the rows of this array are your eigenvectors. But remember, our convention is that the columns should be eigenvectors. So we need to transpose this array. So what we're going to do is we're going to pass in PCA.components underscore dot transpose. And again, we're just going to project out of the first 2 components. All right. So that's our projection, and now let's do the plot. Oh, misspelled that. And then one last thing. So we calculated the explained variance here using our own calculate explained variance function. But scikit-learn already has this implemented for us. So let's do pca.explained variance ratio, and we can see this is pretty much the exact same number that we got. So we're going to use this instead just to make sure that there are no errors in our calculation. All right, so let's look at our plots side by side. So I'll scroll up to my plot. We can see that it looks pretty much the same. However, it looks like it's been reflected over the y-axis. And the reason for this is that scikit-learn does this extra post-processing on the eigenvalues and eigenvectors it calculates, where basically it will check each eigenvector, and if the component with the largest magnitude is negative, it multiplies that eigenvector by -1. So it flips it 180 degrees. And so clearly we can see that our implementation is correct, but just to be extra redundant, I'm going to go ahead and do the same thing with our eigenvectors and make sure that the pictures are exactly identical. All right, so let's close this out, and we're going to go up here and we're going to make one more function. So I'm just going to call this standardize largest components. So we're going to take in our array of eigenvectors, and you know what, we'll just call this eigenvectors to be specific, and we're going to get back the exact same array, which we've standardized in the same way that scikit-learn does it. So largest eigenvec indices, or component indices. So here we're going to calculate where are the indices of the largest components for each eigenvector. So to do np.argmax, np.abs, eigenvecs, axis equals 0. So let me explain what we're doing here. First thing we're doing is we're doing np.abs on our matrix of eigenvectors. And so that means that every component is going to be positive now. It's because we're looking for where are the indices of the components of each eigenvector, which is largest in magnitude. We're going axis equals 0 because imagine we're going down along this axis because each column is its own eigenvector, right? And so what this is going to give us is it's going to give us the row index for each constituent column of the index where the component with the largest magnitude occurs. And so these are just the indices, right? So we want to actually recover the value itself because we want to check its sign. So we're going to do largest vec, I'll do eigenvec, components. This is equal to, we're going to do largest eigenvec component indices. What did I miss? Oh, I misspelled it up here. And then we're going to do np.arrange 0 x.shape 1. So, not x.shape. I'm so used to calling these things x. eigenvex.shape. So what we're doing here is we are going down each row. So we're finding the row index corresponding to the largest component of that individual eigenvector column. And then we're going column by column and extracting out just that value. And so now we just want to find the signs, right? We can do this pretty easily with np.sign on this array up here that we just created. So we're going to do np.sign largest eigenvec components. Largest eigenvec components. Is there something I'm missing? Eigenvec components. Okay, I mean, looks like I spelled it right. I'm not sure why the IntelliSense isn't working. Let me just copy paste this in. Maybe I'm missing like a letter somewhere that I can't notice. Okay, I don't know what's going on there, but we're gonna do return largest vec component signs times x, or times eigenvecs. All right, I think the IntelliSense is just freaking out there, but basically what this is going to do is this is going to give us the sign of the largest component of each eigenvector. And so what we're doing here in this final step is we are just checking if the largest component of an eigenvector is negative, and if it is, we multiply by -1 to flip the direction of that vector so that we're corresponding to what scikit-learn is doing. All right, so this is the moment of truth. So I'm going to clear all of our outputs and I'm going to restart just to make sure that our variables are the same. And now let's go ahead and let's run all the cells above this just to make sure that we've got everything that we need. And so we're going to do the exact same thing. So we've got scaling, we compute the covariance matrix, compute our eigenvalues and eigenvectors. We're going to do one final step though, and it's that we're going to apply that function that we just wrote, this standardized largest components function, to our eigenvectors so that they're exactly the same as the ones that scikit-learn is dealing with. So we're going to run that. We're going to do the sorting. We're going to calculate the explained variance, redo the projection, and we're going to do the plot. And now it's looking like what scikit-learn got. But let's just rerun the scikit-learn pipeline to be safe and make sure we're doing what we want to do. All right, cool. Now let's look side by side. So here is the scikit-learn implementation, and then here is my implementation. And if we look at it, we can see now that it's exactly identical. So we used the out-of-the-box scikit-learn implementation, and we compared it to ours, and we're getting the exact same thing. So we have successfully implemented principal component analysis from scratch on the iris dataset using just Numpy operations. And so I hope you found this video instructive. If you did, I'm going to try to make some more ones. I'll do a theoretical analysis of principal component analysis, but yeah, that's about it. Have a good one.